Okay, folks. Good to be back with you. As you know, I'm not very good at this meeting. And sorry about all the visual noise you see. Not sure what's going on. But when you reduce my head size, luckily it don't look as bad. And I think you do see the screen pretty well. As you know, it takes me a time to get the right files open. I don't know how to open them pre and get them to work. So let's see what we got here. Okay. Yeah, I fumble around more than normal this morning. Sorry. We're getting there. I'm getting there. Okay, so I finally got the slides up, so I'm going to share them with you. All right, I'll put maybe get rid of some of this at the top of the screen here. Okay, Chapter 8, Vapor Systems, Vapor Power System. I'm just going to cover part of this chapter. We don't have time to go through the whole thing, and that's beyond the scope of this course, but I just want to give you a initial introduction into vapor power systems because a lot of you guys or some of you guys may end up in power generation, and as of now the vapor power system produces more power than any other. The learning outcomes, we're just going to learn the vapor. And I'm going to use the slides a lot this morning. Explain the basic principle of vapor power and develop and analyze some of them is the biggest thing we're going to do. We're going to learn how to sketch the TS diagrams, evaluate the property data, apply the mass to energy and entropy balances, mostly mass and energy, some entropy, but not a lot, and determine the cycle of performance, thermal efficiency, net power out, mass flow rates. We're going to determine all these things from the basic power cycle. We're not going to get into varying key parameters and look at their effects. And we're not going to get into this exergy. We didn't study that chapter. All right, so let's get started. First thing, introduction of power generation. Got 3 or 4 slides here. Of course, the purpose of power generation is to meet our national power needs and the challenges. And some of the challenges currently related to power generation is declining non-recoverable supplies of non-renewable energy, such as oil and gas. But that has been largely offset in the last 10 or so years by hydraulic fracking. As you know now, the United States produces as much or more energy than Saudi Arabia and Russia and some of these other countries. And it's mostly been enabled by innovative engineers learning how to get more natural gas and oil out of some of the older oil fields using hydraulic fracking. Of course, there's some environmental concerns, and fracking in some states, such as New York, state of New York, is prohibited. Their neighbor, Pennsylvania, has a very let's say a very big fracking industry and producing a lot of natural gas and some oil. Of course, one of the other challenges of power generation is power generation tends to pollute the environment, and we know the effects of climate change, environmental and human health and safety issues are a big concern. We also know we have an increasing demand for power, especially in countries like China and India, some of these rapidly growing countries. But in the United States, the growth for electrical power is positive. It's increasing a few percent a year, but it's the growth has really slowed down as we become more energy efficient. And today we're heavily dependent on coal, natural gas, nuclear, which are all non-renewables. Now, if you look over in this table 8.1 over here, it lists where we get the sources of our current sources of power generation. This is out of date. So what I did, I made up another slide. Well, let's look at this one first. The type of cycles we use to generate our power, type of thermodynamic cycles, is interesting. Coal fuel, Rankine cycle; natural gas, the Brayton cycle, which we'll study in chapter 10. Nuclear fuel is a Rankine cycle, and oil fuel is a Rankine cycle, and biomass is a Rankine cycle, geothermal, solar. As you see, the Rankine cycle is really still very prominent in our power generation. And we also call that the vapor power cycle, but it's the Rankine cycle. That's the same thing. Okay, here's the little chart I put together and updated it just the other day. Here's our sources of power generation, latest information I got from the web. Natural gas has moved up to 39% of our power is generated with natural gas, and it's increasing that percentage. Coal is down to 23% and decreasing. Nuclear is 20% and decreasing. Renewables are 18% and increasing. But the natural gas cycle is, of course, the Rankine and the Brayton cycle. Coal is all a Rankine cycle, and nuclear is the Rankine cycle, which we're going to study. Renewables, here's the way they're broken down. Hydroelectric, due to dams, is remaining steady. You're not building a lot of new dams, and that's being sarcastic, not building any. So it's staying the same, about 7% of our total. Wind is climbing, it's about 7%. Solar is climbing, it's only 2%. And there's some other miscellaneous, like geothermal and some of these other very small amounts. But you can see renewables, this is the 18%, how it's broken down here. Still only 18% renewable. This will grow some over the years, but we still really dependent on thermodynamic cycles to generate our power. Renewables, like I said, are growing, but in my opinion, I don't want to get political, but the Green New Deal that some of the Democrats are talking about of completely eliminating fossil fuels, which is the natural gas, coal, and nuclear. As you can see, you got a long, long way to go to get renewables up to 100%. And there's just not enough, in my opinion, land to turn into solar collector or places to put windmills that it's going to be 30, 40 years, just in my opinion, till we get up to the point where renewables are even producing a majority of our power, much less the total power. And I think the only way, of course, the goal is very commendable to go to renewables and eliminate carbon emissions from power generation. That's very noble. But in my opinion, and I don't want to get political here, the only way that that's going to happen is if we increase significantly nuclear power. And as you know, nuclear power, because of the incident in Fukushima, or whatever it's called in Japan, is really taken a really hard reputation hit. But nuclear power, again, in my opinion, can be generated safely, and the only way we're going to get to no carbon emissions in any time soon is in my estimation or my opinion is to increase nuclear power. Now, of course, it has to be done safely. It's very expensive. And right now, our best way to produce electricity is with natural gas. It does emit some, but it's way less than coal. I think, and natural gas combined with Rankine's, natural gas is mostly the Brayton cycle, which we hadn't studied yet. When you combine it with the Rankine cycle in a combined power generation configuration, you really have a nice setup. And we're going to talk about that later. And again, you saw table 2 that shows the different cycles. Let me just go back through it real quick. As you can see, in the non-renewables, which is all the way down to here, Rankine cycle and the Brayton cycle, and we're going to study both of those. Chapter 8 is the Rankine cycle, and just portions of the chapter we're going to study. Chapter 9, and again, let me stress, the title of this is Vapor Power Systems, but the predominant vapor power systems, or perhaps the only vapor power system that we'll study, is the Rankine cycle, R-A-N-K-I-N-E. There you go, Rankine cycle. Chapter 8, we're going to study the Rankine cycle. Chapter 9, another video, we'll study the Brayton cycle and the combined cycle. Finally, in Chapter 10, we'll talk about air conditioning, refrigeration, and heat pumps a little bit. 8, 9, and 10, we'll finish the course up, and we'll just cover certain aspects. But I thought trying to cover things I think are important to you to have a basic understanding and might be interesting to you as electrical engineers. Some of you may end up employed by energy or in the power generation field. All right, here's another slide, talks about the alternative vapor power configurations. Fossil, of course, fossil fuel plants, that's a coal. Pressurized water reactor, that's nuclear, we'll look at that. Concentrating solar thermal power plants, we'll look at that, and geothermal. We'll look at all of these a bit. Oh, in each of these types, a working fluid is alternatively vaporized and condensed. And generally that working fluid in 99% of the cases is water. And by being able to take water and turn it into steam, put the steam through a turbine, condense it back to water and recycle is what makes a Rankine cycle such a predominant in today's power generation field. So we're going to go through several slides here. Here's a slide of sort of the configuration of a power generation plant using combustion, and which the combustion could be natural gas or could be oil. But here are the components here. We have the boiler, the turbine, which drives the generator, going down through the condenser to a pump, and this is the thermodynamic cycle here. Some of the auxiliary stuff going on is in the boiler. If you're using combustion, of course, you need fossil fuel and air, coal and air. You have combustion gases, and these go out to smokestack. And if you see such a power plant, and their energy has several, you will see a smokestack with the combustion gases coming out that meet EPA regulations, by the way. Then you also see another big tower too. This is a cooling tower. The cooling tower is used to provide cooling water to help the condenser take this hot vapor coming out of the turbine and condense it back into water, where you can now go back through the boiler. And these two water flows here, the Rankine cycle here and the cooling tower flow, they never never meet. They just they're in close thermal contact, but not in physical contact. This loop here you won't study much, but you're getting thermo 2. You would study that. Of course, you don't take thermo 2. But a cooling tower is probably a third, has a water sump down here, and it picks the water up, goes through, and then picks up the heat in the condenser to cool the condenser, and then come back, and then it's sprayed in a vapor form. And this vaporized cooling, as this water vaporizes, it has a tremendous cooling effect. And so it tends, then it vaporizes, then condense back into the sump here, and it's nice cool water. Now some of the water does vaporize, and if you see a cooling tower and you see, looks like smoke coming out of it, that's just water condensation or vapor, water vapor coming out. It's not, doesn't have any kind of negative impacts on the environment at all. And there, like I said, there is a little makeup water. You do vaporize, lose some water. There's about a 5% makeup water you inject into the system. Nice little system. We use these, industrial plants use these all the time. We had 3 big cooling towers at Eaton to cool our test stands where we had a lot of heat generated. All right. In a nuclear power plant, this part of the circuit is the same with the cooling. The turbine is pretty much the same, although usually they use a 2-stage turbine, a low stage and a low pressure stage and a high pressure stage. We won't be able to get into that. I wish we could, but we're just going to study the basic turbine. And then here's the nuclear part here schematically. Of course, you have the control rods, and this nuclear reaction here is heating this, and this could be a salt, or some kind of medium. It could be probably pressurized water. And you see, here's the boiler. Now the pressurized water that has some nuclear, what's that? It's nuclear. I don't say contaminated, but it has some nuclear radiation. It is, I guess, radioactive is the right word. So it's not allowed to touch the boiler here. It's a heat exchanger, but it's so hot that it creates the steam, and then you have the conventional Rankine cycle. Now, what we're doing, by the way, we talked about these different, the fossil fuel vapor plant, pressurized water reactor, concentrating solar, and geothermal. We're going through each of those. We've gone through the combustion here, and this combustion process could be, the combustion energy could come from usually coal, sometimes natural gas, but natural gas is not typically associated with a Rankine cycle. It's a Brayton cycle we'll get to. Here's the nuclear, talked about that. Now here's the solar. This is pretty new. I'd say new, probably in the last 5 or 6, maybe 10 years. I had a friend who got her PhD in mechanical engineering at Mississippi State, a lady, a very smart lady named Emily Spade, S-P-A-Y-D-E. She did her PhD dissertation on using a solar collector here to provide the heat for a Rankine cycle. But you have these, you've taken in the sun, the energy from the sun, and using to collect the heat through these solar collectors and apply it to a molten salt. Sort of like the nuclear reactor here, where you have this molten salt or pressurized water or whatever, this circuit here heating up the boiler. Well, in this case, all the heat comes from the sun. It's concentrated, melts this salt. The salt goes through the heat exchanger, and this heat exchanger is actually the boiler. And although these Rankine cycle stream and the molten salt stream do not touch each other, physically they're in close thermal contact, and you get a lot, that's where your heat comes from the sun. I don't know, well, I guess I don't know a lot about this. I wish I think I'm going to contact Emily and ask her if I can read her dissertation, see how that came out. I think actually she was, instead of using water, she was actually using some refrigerants in this circuit here. But anyway, this is not too much in use. You like the problem you have always with solar. It just takes so much area of solar collectors to absorb enough energy to be significant. So, but hopefully this process will come along. Geothermal. I got an interesting story, and I try to inject some of this stuff that may be interesting to you and make this a little not so dry. But when I first started with Eaton back in the mid 70s, we here in Jackson, uh, we were part of Sperry then, Sperry Corporation, and Sperry had a big research center up in the Northeast somewhere. And they were convinced there was a real market for geothermal energy. And there was some funds available from the government. So the research center and Sperry's Research Center handed off they did an initial feasibility and decided it was very feasible. And they handed off the actual production of the main component in a geothermal system, the downhole pump right here. They handed that off to Eaton, or it was Vickers then in Jackson. And this pump looks pretty simple on this schematic, just a little round dot. But the actual pump itself was really, really technically challenging. First of all, it had to go down hole in a drill well and by the way, the way these systems work, geothermal systems, there's hot water down below the surface. It's heated by the rocks or the structures down below. It's just natural hot water down there all the time. It's sort of like a geyser, like Old Faithful. Uh, that's just a outpouring. The eruption is from a geothermal source down under the Old Faithful place or whatever. So, but these pumps had to go deep down hole, and they had to pump this geothermal water, which is heavily contaminated, not with bad stuff, but with minerals and particles and rock particles and all kinds of corrosive stuff. And so the pump had to be just tremendously bulletproof. And to get the power down to the pump, it had a turbine on one end powered by steam. So you would inject steam down hole to drive the turbine. Little miniature steam turbine, all about 12 inches in diameter. It was connected on the same shaft to the pump. And then the pump would pump up this hot liquid, go through a heat exchanger, then return back to the well, and it would go through, this would be a boiler. The water would never touch the Rankine cycle water, not physically, but thermally they were in close contact. So you transfer the heat from the hot geothermal fluid into the boiler, produce steam, and go on with your conventional Rankine cycle. We spent millions of dollars on that and finally developed a pump. It was about, I would say, about 3 feet long and probably 1 foot in diameter, and it was full of mechanical engineering technology. And we got that pretty well developed, and about the time we were ready to go in production with it, the market just dried up. Not sure what happened, but we had a pump and we're trying to get partners in the oil or in the energy business to help us drill a well where we could get started, and we couldn't find a partner that wanted to work with us, and that whole program just evaporated. It's a shame because a lot of engineering went into that. All right, now what we're talking about here looks like this is back to the combustion gas. Okay, we're going to now start going into the major subsystems and the Rankine cycle. So we're going to look pretty much at the typical cycle, which uses coal uh, or natural gas to fire up the boiler, mostly coal. So we'll go through each system and explain it a little bit to you. As you see, the final output is an electrical generator generating three-phase electricity that goes out to all the homes and businesses and so forth. So pull this down. This is, they call it subsystem A. This is the boiler, and I'm gonna have to read that to you, sorry. Provides the heat transfer of energy needed to vaporize water circulating in subsystem B. Subsystem B is pretty much the rest of the Rankine cycle. In fossil fuel plants, this heat transfer has its origin in the combustion of the fuel, generally coal. All right. In subsystem B, that's really what we're studying here. That's the Rankine cycle we study. We have the boiler that produces a hot steam, hot pressurized steam, goes through the turbine, produces shaft power to drive the generator, mechanical shaft power out, and then once you've got as much energy as you can out of that hot, high pressure steam, it comes out of the turbine as low pressure, usually a low pressure vapor with a quality of 90, 85, 90%. So it's a mixture, but it's mostly vapor. And so to get it back ready to go through the boiler, you have to go through the condenser. And it does what? It condenses from a vapor to a liquid, so a saturated liquid. Now this is part here is low pressure, maybe 1 bar. The boiler's high pressure, maybe 80 bar. So this pump pumps this liquid from an inlet of 1 bar, pressure of 1 bar, back up to the pressure of the boiler, which could be 80 or 100 bar. Okay. The electric generator, we won't talk about that. I'm sure you guys will get it in electric machines, but it's quite a interesting apparatus. We use a lot of electric motors at Eaton. Of course, electric motors, electric generator in reverse. Instead of producing power, we absorb power in our motors, use them to drive our pumps for test purposes. But this all ought to start looking pretty familiar to you now. Subsystem D. Okay, that's the cooling tower. I explained that to you. It's a really economical way to provide the cooling to cool this water entering this. What's the temperature? Well, it's not a very high temperature, but it is mostly vapor. It's probably 100 degrees, 100 degrees centigrade, but it has to be converted into water, liquid for the pump. Pumps don't pump vapor, just like compressors don't compress liquid. Compressor for gas, pumps for liquid. And again, this is a separate loop. We don't study this much, but it's pretty simple. We had 3 cooling towers at Eaton, and we could run the shop with 2. So if one went down, we always had enough cooling water to keep our tests going. This is I did a lot of work on reducing the energy consumption of this system. We had 3 towers, had 3 circulating pumps, each one of them, I think about 100 horsepower, and we converted to variable speed. We saved a lot of electrical energy in this system. Okay. I think that's all right. Each unit of mass of water periodically undergoes a thermodynamic cycle as it circulates through the components of subsystem B. This is the Rankine cycle. And as you know, this is a continuous circulation. We take snapshots at different states, say coming in the turbine, going out of the turbine, coming in the condenser, going out of the condenser, coming in the pump. We take snapshots and determine the properties, but this whole process is continuous. It doesn't stop unless they have a mechanical issue or a problem with one of the components and have to shut it down. So now let's look at the Rankine cycle. Let's see how many slides we have. Well, we have a lot, so I got to go move along a little faster. So basically, if you look at the Rankine cycle in a box here, you know we draw these diagrams a lot. From the hot body here, which is the combustion temperature, we drive in heat into the system. And from the condenser, we're taking heat out. The difference between the heat coming in and going out is converted by the turbine to work. And so the work of the cycle, and he uses negative sign. Q coming in is positive, going out is negative. I would like to put a plus sign here and then let the direction of the heat transfer take care of whether it's plus or minus, but they use the minus, so just be sure that QN, you take the difference between these two if you get confused. The thermal efficiency of this cycle and the philosophy behind this thermal efficiency definition is you have to pay for this QN. That's your biggest cost, the fuel cost. So your efficiency is how much of this fuel energy you convert into work energy. That's what this means. Work of the cycle. Now, why doesn't it say the work? Why doesn't it just say the work of the turbine? Because there's a pump over here in the system that takes some energy. Now, it's a very low amount. It's maybe 1% of the turbine output. Now, this turbine does not drive the pump. The pump has to be powered by a separate electric motor, but it does consume some work for the system. So if the turbine outputs 100%, say 100 megawatts, less than 1 megawatt will be required to drive the pump, but it has to be accounted for. A lot of red writing here. Let's see if we can skip this one. Well, what that says is because of the second law of thermodynamics, you're limited by how much this thermal cycle could be. This is TH, this is TC. And as you know, Carnot says that the maximum efficiency of the Carnot cycle is TH minus TC over TH. And that may be 70, 80% limit just by the temperatures you've got access to. The temperature you got to drive your heat in, the temperature you got to pull the excess heat out. We'll look at this a little later, but the thermal efficiency is limited by the second law of thermodynamics. That's what all of this said. Now, that's what these two said. Now, there are many, many ways to improve the thermal efficiency of a Rankine cycle, and they're in practice today. We won't be able to get into those, we just don't have time. But the point of this slide is no matter how many improvements, if you calculate your Carnot efficiency and it's say 75%, and you're running here at about 40%, well, there's nothing you can do to get above the 75%. Never going to happen. But 1%, 2% improvement is really significant in the amount of money you would save. So it's really very cost efficient to make improvements. You're just never going to get above the Carnot improvement. Now, let me say this, even if you've got let's go to the next slide. Let's say you calculate the efficiency, thermal efficiency, using that little simple equation. By the way, that simple equation takes a good many calculations before you get to the before you get to that point. Here it is. Before you get here, you've got to calculate all the enthalpies to get the works. You've got to you end up having to determine the enthalpies and the mass flow rates throughout the system before you can make this little simple calculation. So, sort of lost my train of thought. I was talking about efficiency. Okay, it'll come back to me. But anyway, sorry about that. I need an editor to edit out all of these snafus, don't I? So here's the Rankine cycle. Here's the basic components: the turbine, the condenser, the pump, and the boiler. Energy, we have heat transfers here in the boiler, heat in, we have heat out here in the condenser, work output of the turbine, and then you got to put some other work, usually a big electric motor. For instance, if this turbine, say, puts out, I'm just say 70 megawatts, well, this pump would take about 1 megawatt of energy. So 1 megawatt, that's 1,000 kilowatts. That's a pretty good size pump, but still compared to the output of the turbine is pretty small. Okay, turbine, condenser, pump, boiler. Now, the way he says all energy transfers by work and heat are taken as positive in the directions of the arrow. I still like to use the algebraic plus and minuses, but he's saying if you draw the arrow and show this work coming out, you can call it a plus. If you show this Q coming in, you can call this a plus. If you show this Q going in this direction, you can call it a plus. You call this work coming in a plus. I think you'll be less confused if you still use the algebraic and keep the plus and minuses. For instance, this is work, this is energy, heat transfer in, it's a plus. This is work out, it's a plus. This is heat transfer out, it's a minus. This is work into the pump, it's a minus. And just algebraically add them. I don't think you'll have any problem figuring out how to combine them. Okay. Through the turbine vapor expand, I wish I could show both of those slides side by side, but through the turbine, the vapor expands through the turbine, developing work. Okay. Through the condenser, the vapor condenses to a liquid through heat transfer to cooling water. And we know the cooling water is generally a cooling tower circuit. Liquid is pumped into the boiler requiring work input. That's the pump. And the liquid is heated to saturation and evaporation in the boiler, evaporating the boiler through heat transfer from the energy source. So it's pretty straightforward. And generally we label these: state 1 is going into the turbine, state 2 is coming out of the turbine, going into the condenser, state 3 is coming out of the condenser, going into the pump, state 4 is going out of the pump into the boiler, and then 4 to 1 is coming out of the boiler and going back into the turbine. So the way we analyze a Rankine cycle, and we've already done them, I know, and so you could legitimately say this is the, I've let the wagon get ahead of the horse here, and that's to some extent correct. But we examine each of these components in the Rankine cycle as a control volume at steady state. We don't try to do transient analysis. To do an analysis, we say the turbine and pump operate adiabatically and isentropically. So the entropy through the turbine is constant, we say, and the entropy through the pump. And that gives us a way to calculate the ideal best case scenario for these two devices. Then we'll be either given state 2, the actuals of state 2, the pressures and temperatures, where we can look them up in a table, or we'll be given the isentropic efficiency of the turbine and the pump, and from that we can calculate what H2 is. We'll see later. We don't, we ignore potential and kinetic energies because they're just not. Now, here's his formulas. Now, the work of the turbine is positive because it's work out. So it's H1 minus H2. Remember, if you can remember in your, let me try to use this try to get this board going here. Come on, wake up. There we go. There we go. All right, I need to share this with you and make sure that I lost my cursor. You may have to just go fast forward here. For some reason I lost my cursor. There it is. Okay. The pen is fighting. Usually they don't fight each other. Okay. Now we're back. Now I got to make sure you can see this. All right, you should be able to see the, all right, I'm going to try to make this legible. But I know it takes a long time, I'm sorry. Remember, the basic way we wrote our energy equation is the sum M exit H exit, oh goodness, minus the sum M, my goodness, H I is equal to Q, the control volume, minus work control volume. So if we're talking about a turbine, this adiabatic turbine, this is 0. And if it's one inlet and one outlet, which is generally the case, we'll have M dot, and the outlet is 2 minus H1 equal minus the work. Now if we want to solve for work, we get M dot H1 minus H2. So that's where he got, and he puts his M dot, so he's getting per pound mass. So that comes out exactly right. But and the boiler comes out exactly right. But for the condenser and the pump, he's got them where they come out positive, and I don't like that. Yeah, if you actually go through the equation and for the pump, you'd actually get H3 minus H4 and come out with a negative number. And then you algebraically combine it with the others. I don't think that's going to throw you off. I would prefer to use, well, maybe, let me try to show you what that is. I'm going to erase this. Let's look at the pump. Let's see. Whoops. Draw a pump here. We got flow coming in, flow coming out, and this would be H2. Well, he's calling that. What's he calling it? The inlet to the pump is 3 and the outlet's 4. If you look at that circuit. Inlet to the pump is 3, outlet to the pump is 4. So I know it's tough to, let me try to draw that again down here. Select the pen. Somewhat better. This thing is almost, I'm almost so. So that's state 3. This is state 4. And if we write the equation, we have m dot. Now coming out is 4, so h 4 minus h 3 equal, and it's q minus w. We'll just put the minus w because we know q is 0. Then if we solve, let's solve for, like he does, w over m. That's work per mass. We would get, now we reverse those since there's this negative sign over here. And what we'd get algebraically is h3 minus h. Oh, and h4 is a higher energy point, so that would come out negative. So you'd get a negative number. And what he does to keep you from getting the negative number, he switches these around, h4 minus h3, and call them positive. And then when he combines them, he subtracts this positive number for this positive number. I don't like doing that. I like to keep them the right sign. So I'm going to require you keep a positive sign if it's work out, and negative sign if it's work in, and just combine them algebraically, and you'll get the right answer. I don't think it'd give you any problem. It sounds more complicated than it is. So the thermal efficiency ends up being the work of the turbine per pound mass minus the work of the pump per pound mass. Or you can put the mass flow, m dot w, you can put it on top, but it's going to cancel out. So you might as well get it per pound mass, because you end up with just the enthalpies. The work of the turbine is H1 minus H2, and the work of the pump is actually H3 minus H4. You get a negative number, and then a negative times a negative gives the positive. What he does, he switches the H's to make them positive, and then puts this one negative here. But all you got to remember is the work of the turbine and the pump are opposite in direction, and they don't add to make a bigger number. They combine to make a smaller number. Then down the QN, it is H1 minus H4. It is a positive number. So the thing I want you to remember here, once you come up with the enthalpies and look all those up, actually making the calculation is pretty straightforward. I'm going to put a plus here, and then I'll have H3 minus H4. That'll give you a negative when I give you the formula on your formula sheet, but don't let that confuse you. Then they come up with this thing called the backburst ratio. That's the percentage of the pump work compared to the total turbine work. And again, by the way, when you calculate these, if you get a negative number over a positive, as long as you've combined them right here, it doesn't matter. The efficiency is, you could draw absolute value around here, bars, if you want to. The backwork ratio is just the power, how much percentage of the turbine work the pump uses. Now again, the turbine doesn't drive the pump. It's a separate electric motor driving the pump. But it's useful to look at what percentage of your work of the turbine has to be provided to drive the pump. And like I say, it's usually less than 1%. In fact, he says the power required to the pump is less than 1%. But it has to be taken into account to get the right number. Okay, let's see if we can. Okay, so since these equations are developed for mass and energy balance, they apply equally when irreversibilities are present and for ideal performance. We'll see what that means in a later. And they talk about some of the irreversibilities. If you look in an ideal performance, you neglect the pressure drops. Um, well, to do an ideal cycle evaluation, and that's a good place to start. The frictional pressure drops are through the boiler and condenser. We neglect those and say the pressure through the boiler and the condenser happens at constant pressure. There actually is a pressure drop, but we're going to say constant pressure. These don't make a considerable amount of losses in a typical system, but the irreversibilities through the pump and turbine do. You need to account for those. So what we'll do, we'll get an isentropic adiabatic power, and then we'll factor that up depending on what the published efficiency of the pump and the turbine are. We'll see. Okay, here's the circle, the process. Now the ideal Carnot cycle is this cycle here, where you go heated to saturated vapor, go down to a mixture here at the low pressure, go through the condenser, come out saturated liquid. In other words, there's no superheat up through here. Well, the ideal cycle has to have the actual cycle won't provide you any, won't work because you cannot drive. Turbines don't like a lot of vapor in their mix in the stream of energy mass going through them. Most of the time, the turbine will accept a little bit, well, the turbine will accept a little bit of water or vapor down as it comes out. But in order to drive a real steam turbine, you have to heat your, the boiler has to go to 0.1 up to 1 prime and get you some superheat. I think that'll make sense when we work a problem. One of the things about this cycle that the pump is over here in the liquid area. Let's forget about this 0.1 and 2. Let's look at the real cycle. The real cycle, say coming out of the boiler, again, you're bounded by upper pressure. This is a constant pressure line here, comes here, and then goes down like this. And then this is a constant pressure line, here. This can be typically 80, 100 bar. This is like 1 bar or less down here. So you come out, you go into the boiler, once you get into the boiler, you hit the boiler pressure. This is a constant pressure line up here, 80 bar. This is in the compressed liquid zone. This is a saturated liquid. As the boiler starts supplying the heat, the liquid starts vaporizing, high pressure vapor, all vapor, high pressure steam, superheated steam. Now it's ready to go through the turbine. Goes through the turbine as superheated steam, goes through, you get a lot of power out of it, drives those blades, and you come out generally as a mostly vapor, but some liquid, a mixture, but with a high quality of about 90%, 80, 90%. Then it goes through the condenser. And then, although this is a really short little line here, there's quite a bit of pressure drop. Pressure increase from this point to this point. You're going like from 1 bar to 80 bar. And then you go through the boiler again. The ideal process is here. This is isentropic. See the isentropic, the S here is constant. The pump process is isentropic, ideal, and then you may be given an efficiency, but the actual process, all work processes have to increase the entropy due to their inefficiency and irreversibilities. So the actual process comes down here and hits this line. It may hit right in here, may hit out in here. It's hard to say. And this is constant entropy. This area can give you some problems here calculating because it's hard to look up these values in the table. Now the problem I gave you said to use a compressed liquid tables, and those values you could look up them in the table we have, but the table's not very good. So there is another way to calculate the isentropic pump energy, and it's the VDP. So you look up the specific, and I could write out the energy equation for a liquid, and I could show you how this is derived. It's not that complicated. I just so hard to do it here without a board. Just accept my word for it that this is very legitimate, since it's a essentially incompressible liquid, that the work of the pump is the specific volume at 0.3 times P4 minus P3. Now again, he's arranged them where he gets a positive number here. I'd like to use and get a negative number and then combine it with a positive number of the turbine output to get the net work. It's actually P3 minus P4. This is easy to look up. You'll be given these two. It's an easy calculation to make. There's some little messiness in getting the units right over in here. You have to convert, but it's not hard. But now that's the isentropic pump efficiency. And you know this work here. So sometimes you actually need H4 in your boiler calculation. This doesn't give you H4, this uses pressures. But, and I wish I was better on this board, I would show you how you get H4. But it's in the book, it shows you what you do, you calculate this amount of isentropic work. You can always look up H3. It's just saturated liquid at this pressure, easy lookup. So H4 becomes H3, which you look up, plus this amount of work, which you've calculated this formula. That's the way you can back into H4. You don't need H4 for this pump work. No, sir, you calculate right here. But you will need H4 in the calculation of heat transfer to the boiler, because that heat transfer in the boiler is m dot times H4 H1 minus H4, so you need H4. All right. All right, this is talk about some areas under the curve. I think we're going to skip this. And we talked about superheat. You have to have superheat for this thing to work right. So let's just skip over that. Now, this is an interesting thing that happens a lot. How many slides we got? 38. So we're getting close. We're on. I just don't want this to take you all day of your time. I'm so. All right. I think I already talked about this one. All right. All right, the point is you've got to go up here in the your boiler's got to heat you up here in superheat for a real cycle to work. Now, I'm not going to give you a problem like this. I wish we had time to do, but this is typically the situation in a real power plant for the turbine. And we saw it on the little video I showed you in class when we were meeting in class. So engineers over the years have found the best way to get the most work, bang for the buck out of a turbine is to divide it into a low pressure turbine and a high pressure, two different turbines connected to the same shaft. And what you do, you go through your high pressure turbine until you get about halfway down your pressure. In other words, if this high pressure, say this high pressure is 80 bar and the low bar is, and the low pressure down here is 1 bar, you might go through a pressure drop of half of that, about 40 bar, through the first turbine and get as much energy out of that 40 bar drop. You got steam coming in at 40 bar and you're going out as steam at, I'm sorry, you got coming in at 80 bar, and when it gets to about 40 bar, you through the high pressure turbine, you drop it out, goes right in here almost from 1 to 2, 1 to 2. That's through the turbine. You go back and just about touch the the saturated vapor line, and then you heat it back up in a separate section inside your boiler, in a reheat section. You heat it back up again to about the same pressure, maybe not quite as high. I mean, about the pressure is low, absolutely lower, 40 bar, but you heat it up approaching the same temperature of T1 to T3, and then you go through another turbine, a low pressure turbine. And experience has shown that this type, separating these out, gives you the best performance. Then you go through the condenser and then through the pump, as so on. So, so this is if you went through just through the turbine from 1 to 4 prime, and if you go for the reheat, you go from 1, 2, 3, and then back down to here. You're able to extract a lot more, convert a lot more of this heat energy. I say a lot more, a significant amount more than if you go through a single stage turbine. Like I said, the problems I'm going to give you are single stage turbines, but I want you to remember that a dual stage is what actually most in use. I wish I had time to do one, but it's not complicated, it just takes longer. So I just talked about the process 1 to 2, steam expands through the high pressure turbine, process 2 to 3, you go back through it, the heat, they call it a reheat steam generator. It's usually in the same boiler, just a different physical part of it. Reheats it, then you expand it, and you can get it when it comes out of this turbine. It's generally almost all vapor, so you've gotten just about all the good you can get out of steam when you go through these dual turbine like this. And they talk about some efficiency and reheat and so forth. It does up your efficiency. Supercritical. I've just taken too long. I'm not going to go into supercritical here. You're welcome to read these 2 slides. It's pretty interesting. I think what we'll try to finish up now, working the problem on test 3 that had to do with a Rankine cycle. So I'm going to exit out of here, and I'm going to go to the test. I don't know if you can see this or not, can you? Yeah, you should be able to see what I'm doing. Go to test 220, test 3, get my key. By the way, I hadn't graded your test 3s, and I'm going to grade them pretty leniently because I know it's 2 years pretty hard and long. I used to go through your test, and I usually honestly find a few errors in my calculations. Sometimes I don't, but usually I do. So I haven't proofed my key yet to see if it's 100% right, but let's look at. And again, it's and a little bit different. Let's look at the turbine problem. Here's the compressor problem. By the way, Kelly, I remember you had a question about the isentropic compressor efficiency. I defined it as, let me get it right now, H1 minus H2. No, that goes, sorry. You can see this is the least amount of work, goes on the numerator, H1 minus H2S over H1 minus H2. The book had it defined, had this switched around, it had the same same components in numerator and denominator, it had them switched around. In other words, it had H2S minus H1 over H2 minus H1. And Kelly, I know that fouled you up a little bit because it didn't agree with the book. But the reason I do that, because the way the equation comes out for isentropic work, it will be H1 minus H2S. For regular work, it'll come out H1 minus H2, and then there'll be negative values because H2 is bigger. You'll get a negative work, which is what you're supposed to get going in a turbine. But now when you take the ratio and get the isentropic turbine efficiency, it doesn't matter whether it's H1 minus H2S over H1 minus H2, or it's like the book, H2S minus H1 over H2 minus H1. Believe me, you'll come out with the exact same answer, and it won't foul you up. So, but it's a good question, Kelly, and I wish I'd explained that in class. Now, let's go down to the, that's the air conditioning circuit. Okay, here's the boiler. Now, let me reduce that in size a little bit. Or here's the Rankine cycle. So we have a boiler here. Let me make sure you can see this. Yep, you're looking at it. So we have a boiler here, and the steam comes into the turbine at 100 bar and 560 degrees. That's actual. You can look that enthalpy up directly. Let's see, what did I say here? I don't want that. I give an efficiency, don't I, here for the turbine? I'd give that somewhere. Where did I give that? I'm not seeing that. Oh, do I have the wrong? No, I have the numbering system all messed up. Oh gosh, where did I put that on? Somewhere it should say that the entropy, maybe I added that to your test later. I'll figure it out, but somehow the H2S. Oh, I know what. I tell you this is isentropic through the turbine, but then I give you the actual state of the actual state too, which you can look up. But I asked you to come up with H2S. I think is how I did it. Well, let's look at the state 2S, isentropic, because I asked you for H2S. This, you'll find that the actual state 2 shows a state 2. The actual state 2, if you look up this, and you can look it directly up, saturated vapor at 0.1 bar. You look it up in the table. Maybe we should do that. I know it's going to take time. All right, let's do that. Okay, it should be on page 929. You probably can't see that yet. All right, now reduce it down. Let's see if you see in that. Yeah, you should be seeing that. Okay, but remember that was doggone it. Okay, I'll be careful not to go down too far. Let's go back to the problem. So state 2 was 0.1 bar in saturated vapor. So .1 bar in saturated vapor. All right, that might not be big enough for you to see. All right. Here's what was it? 0.1 bar. Here's 0.1 bar. If you see the cursor, go over here to HG, saturated vapor. Saturated vapor should be 2584.7. On my screen, it just went away. Oh gosh. Goodness. I don't know what you see now. Somehow I lost my screens. Now I did it again. All right, I'll have to go at one at a time. But anyway, 0.1 bar should be 2584.7. I need to figure out how to get that other screen up there. Doggone it. All right. 2584.7. Let's see if I'm going to have to pull them up one at a time now. Oh, there we go. Okay, it's back. There it is, 2584.7. But the entropy is 8.1502. Just look it up as SG. So I got both entropy. But now the entropy at state 1 was 6.87864. So that's an increase in entropy. So that's H2. If I'm looking for H2S, which I ask you to calculate, I'm not sure why right now, I'm looking for the entropy, the enthalpy, where the entropy was constant at 6.7864. So how do I do that? All right. Well, I know the entropy is 6.7. What do I know about state 2S? I know the entropy is the same. It's got to be 6.7864. What else do I know? I know it has to be the pressure at 1 bar. Or 0.1 bar. The pressure is the same in the isentropic state. So it's 0.1 bar. So my entropy has to be 0.7864. So I go over here to 1.1 bar. Look at the entropy of gas of vapor is 8.15. Entropy of liquid is 0.64. Our actual entropy is in between those. So it's a mixture, and we have to calculate its quality. So that's what I did here. I found the quality at state. I know the entropy at state 2 is same as state 1 at state 2s, but I see it's a mixture, so I calculate the quality is S, which I know from state 1 minus SF over SG minus HF. These all come from the 0.1 bar. Then I get 0.8182. Now I can calculate H2S directly as HF plus X of 2S, the quality, times H of FG, and I get whatever I came up with. 2146.9. So that's the way I got. That's where this 2149.6 should be what I got. Did I not get that? I've been known to write the 2149.6. Okay, so I got the right number. And that's the way you do it on a steam turbine. On a air turbine, it's a little different. So I have my H2S, and I know my S2S is by definition the same as S1. H3, I can look that up directly from the conditions. That's what we just looked up, is H3. Now H4, I said to use the compressed water table because we haven't used those much. And you just have to interpolate. Let's go to that. That's probably about 9. What page did I say that is? H4, 935. Let's go to 935. Compressed water table. What do we know? That the pressure going in the evaporator, the high pressure side is 100 bar, and we know the temperature is 48 degrees. So we don't have, so like I said, you know, the graduations in this table is not very granular, as they say. Here's a 100 bar in compressed liquid table. There's only one page or so to it. Here's 40 degrees and 80 degrees. So our H is between these two numbers, 40 degrees and 80 degrees over here, 100 bar mini table. So we have to use our advanced interpolation skills. H4 is this formula, y1 plus dy dx, x minus x1. Y1, okay, y1 is 171. Where did I get 176? Did I do that wrong? 176.38. 342. Oh, I'm on the wrong. I got you. Here I am. So it's y1, which is 176.38 plus dy dx. That's dy is 342.83 minus 173.38. And dx is 80 minus 40. Then times x, the actual y times y1, or x times x minus x1, 48 degrees minus 40. And if I calculate that, I get I get H, and I did the same calculation for entropy, same interpolation. Interpolating, I got 209.67. For H, I got 0.6822, because S is given in this same table. So it's, see, there's so much graduation here, 40 degrees, then it goes to 20, 40, 40. The table is not fine enough, doesn't have enough values to be useful. But I wanted you to get some practice with it. So that's how you find H2S in this case. You weren't given a isentropic efficiency. You were just given the actual points and asked to count. You were given the actual points coming out of the compressor, which was this. That's H2, and you're asked to calculate H2S. And to do that, you had to realize the entropy at 1, at state 1 here is equal to state 2, and you had to go interpolate to get that. Here's how the diagram looks. Pretty rough looking drawing here. But the main thing to remember is there's 2 levels. The low pressure here was 0.1 bar. The high pressure here was 100 bar. The boiler takes this and goes along this constant 100 bar pressure line. The saturation temperature here, where the pressure and temperature are the same, is 311. As soon as you hit here, you start going up in temperature at constant pressure now, all the way constant pressure, superheated zone. And then the isentropic expansion, this should be a straight line, vertical line, and I didn't draw it very vertical, but that's where entropy is equal to constant, and it turned out to be a mixture about what, about 88% or something. And then the actual H2 I gave you in this case, which is right here at 0.1 bar in saturated vapor. Then it goes through the condenser and condenses and comes out as saturated liquid at this same pressure. And pumping it up to this high pressure here, like I say, this is a short line, but it's a lot of pressure increase going from 0.1 bar to 100 bar. This is the isentropic pumping action. The actual pumping action would be the entropy would be increased. It'd come along in here. I didn't ask you to calculate that. Okay, so we're going to wind up now. I've taken enough of your time. The next video I'm going to do, I'll probably do it today, is chapter 9, where we combine the Rankine cycle with the Brayton cycle. I wish I was here to answer your questions. I wish I could explain this better. I wish I could use all of these things and all these screens and everything. I wish I could go faster, but you know, that's what you're stuck with. So we just got to do the best we can. I know you're doing the same thing. It's not ideal for you guys either. So I'll stop here. Once you view this video, if you have any questions, text me, email me, call me, or whatever. But I hope you have a good day and stay safe. All right, I'm going to stop here, and you should be dropping out shortly. Goodbye.